We have some definitions that are important here. We have a definition that two vertices are adjacent if there is an edge between them, and the degree of a vertex is the number of other vertices that are adjacent to it. We could give ourselves a challenge here. Let's look at a description of different degrees, and let's see if we can draw a graph that matches this description. So here I'm asked for one vertex of degree 1, two vertices of degree 2, and one vertex of degree 3. And here I have a diagram for a graph that satisfies this property. And now, of course, our natural question is, but is this the only one? Can you find another diagram for a graph that has these properties? Is that graph really different? Well, we could say, well, of course we can find a different diagram that has the properties. We could draw this diagram in a different way. Can we find a different graph that has these properties? Well, we could just erase the labels we have and change them. If we find a graph that has these properties that looks really different, in addition to a diagram, we can describe the degree sequence of a graph. So this is a sequence of numbers, which is an ordered list from smallest to largest of all of the degrees of all of the vertices in your graph. If you have more than one vertex that has the same degree, you repeat the number. So the first thing I want to do is calculate here the degree of A. I see A is in 1, 2, 3 edges, so the degree of A is 3. And then I do the same thing for B, C, D, and E. After I find the degrees and put them in order, I have the degree sequence. So the degree sequence of this graph is 2, 2, 3, 3, 4. We can do the same thing with a diagram. It's not hard. If I look at the vertex Z, see there's one edge, and this has a degree of 1, and X has 2 edges that it is incident to. So X has a degree of 2. And if I take each of these numbers and put them in an ordered list, I get the degree sequence, which is 1, 1, 1, 2, 3. We've seen how to take a graph and get its degree sequence. We can go the opposite way. We can ask, if you know the degree sequence, can you figure out the graph? I might try this. I might see if I can start sketching one out. Figure out after I try it. No, wait a minute. In this graph, there's a vertex with degree 5. And I'm asking for a simple undirected graph, which means if there's a vertex of degree 5, there must be at least 5 other vertices. And that can't happen because I only have 4 other vertices. So in this case, I can rule out the existence of a graph that has such a degree sequence because the largest degree is too large. Now let's look at a different one, and let's say 4 1s, 3 3s. Can you find one here? And here the largest degree is 3, so I can't rule it out based on that. I might start playing with it, and what happens here when I start playing with it is kind of interesting. I start trying it, and I sketch one, and I can't figure out how to connect it up. And then I try again, and I get close. I get a graph here that has a degree sequence of 1 1 1 3 3, which is almost what I wanted. I wanted 1 1 1 1 3 3 3. So this is really close, but it's missing this last 3 on the end. Unfortunately, this is not one of those situations where I can extend my partial progress, because as soon as I try to put another vertex in here and connect it to anything, it's going to change some of these numbers. So then I start to wonder, maybe this isn't possible. And in fact, I can use something called the handshaking lemma to prove that this is not possible. So I have the handshaking lemma over here, but unfortunately, when I wrote it and scanned it, the scanner cut off a really important part of the formula. So the handshaking lemma says if we take the sum over all vertices of the degrees of each vertex, or the sum of all of the degrees of all the vertices in the graph, and what we get is 2 times the size of the edge set, twice the number of edges. But let's accept that this fact exists and that it is true. And let's see how we can use this to prove that there is no degree sequence that has 4 1s and 3 3s. Let's look at the sum of all of the degrees. So we have 4 1s, 3 3s. And the total sum of the degrees will be 13. But on the other hand, that has to be equal to twice the number of edges. And you can't have 2 times an integer be equal to 13. So this is not possible. But past that, it gets more subtle. So I could ask a question like, find as many different simple undirected graphs as you can with these degree sequences. Let's look at the first one, which is just 1, 1, 2. Well, what does different mean here? We saw different graphs can have exactly the same structure. And so I can say that there are infinitely many different simple undirected graphs with degree sequence 1, 1, 2. I'm going to define an infinite set of graphs indexed by k. And for each graph, the vertices will be 3 times k, 3 times k plus 1, and 3 times k plus 2. And I will put an edge from 3 times k to 3 times k plus 1, and another edge between 3 times k plus 1 and 3 times k plus 2. So what I'm doing here is I'm generating graphs that look like this. The first one will be 0, 1, and 2 with 0 adjacent to 1 and 1 adjacent to 2. Then the next one will be 3 adjacent to 4, 4 adjacent to 5. And each of these will be different. I can keep doing this forever. And this is infinitely many different graphs that all have the same degree sequence. So maybe that's not what I really mean. Maybe what I really mean is something like I need a different definition of different. So this is annoying. I shouldn't get to do this infinite cheat, say there are infinitely many different ones. Although that's true, I need a definition that captures the idea that in this instance, two graphs that look structurally the same, is there a way that I can consider them to be the same? Like if I have 2 apples and 2 rocks, I don't have the same thing. But the number 2 is used to encapsulate both of those ideas. Is there a way that I could say, well, this graph is structurally the same as this graph? There is, and that's going to be a concept we come to later called isomorphic. So even though this ABC graph and this 1, 2, 3 graph are not the same graph, these graphs are isomorphic. All I'm going to say about that for now, and we'll come back to it at another time. What I want to discuss then is maybe we should change the question. In mathematics, if you realize that you asked a wrong question, you don't have to be afraid to change it. The question we really wanted was to investigate if we're given a degree sequence, can we come up with a graph that has that degree sequence? So why don't we ask that instead? Instead of saying, can find as many of these as you can, let's just say, can you find one? Now, this is a good thinking exercise, and I encourage you to work through these and see if you can or cannot find graphs with these degree sequences. But the big thing I wanted to emphasize there is that often we're given a question in a class and we think, well, we're stuck with it. And that's really not how mathematics works. If you ask questions as a tool towards getting insight, and if you realize you asked the wrong question because it has a trivial answer that doesn't give you insight, try changing your question.